I'm a senior econometrician in the Research and Impact Assessment Division in the Strategy and Knowledge Department. And I'm very happy to be here, and I thank the Office of Evaluation for inviting me to be the rapporteur. I'm very pleased to introduce Paul Jasper from Oxford Policy Management. So Paul is a development economist with an extensive experience in survey work, quantitative research, experimental and quasi-experimental quantitative evaluation methodology, and statistical analysis. So he's particularly interested in methodological advances related to quantitative impact evaluation and the application of big data analysis in public policy. So he holds a Master's of Public Administration and Public Policies from LSE and the RT School of Governance in Berlin, and also is a track record of impressive academic qualifications. And so I really look forward to his talk. And without further ado, I'll pass the word to Paul for his presentation. Thank you.
Here, and I hope that this still works for everyone. Before I actually start, I think it would be nice to put this presentation into the context of the conversation that we just had, and I think that works actually quite nicely, because at the panel discussion that we just had earlier, there was this discussion about theory versus big data analysis and causal inference versus big data analytics, right? The fact that a lot of big data analytics is about prediction, and that doesn't really help you to solve sort of questions about causal impact. Now, this is actually a topic that I was always very interested in as well, and that's what this presentation really is about. It's about thinking or presenting what sort of new approaches, new ideas have come up in the literature, and what sort of I also have started to use in my work to, despite having this separation, to use methods that come out of computational statistics or out of big data analytics or whatever you want to call it, to use those in the context of experimental and quasi-experimental impact evaluations. Because I think that despite the fact that these computational methods have a slightly different perspective normally on certain issues, they can still be used in a productive way. So what I'm going to talk about today is I'm going to start this is going to be relatively methodological in that I'm going to start with a discussion about what I think big data is and what actually is the new and interesting thing about these methods in big data analytics, and how they compare to traditional methods in econometrics. So what's different about them, and why do they not help us with inference and causal inference, right? After that, I'm going to briefly summarize sort of core strengths and weakness, and then I'm going to talk about, well, but can we still do something with these methods? How can machine learning approaches be employed to help with causal inference? There's an emerging literature on that. I'm basically going to summarize what others have said about this and what others have published about this. And then I'm going to finalize with an area where I think this is very useful and where I have also used machine learning approaches, or tried them at least, in quasi-experimental impact evaluations. And then I'm going to conclude. And then hopefully there will be some time for questions and answers and discussion, of course, in the end. So just to start, by training, I'm an economist and econometrician. Until very recently, big data analysis, machine learning was not on the radar of any economist, really. I mean, certainly when I was at uni, I never heard about it in my quantitative methods classes, right? But that, of course, has changed. Recently, in 2014, Halvarian published this article in the Journal of Economic Perspective, which is called Big Data, New Tricks for Econometrics. That caused a lot of fuss. People started to look into these methods. This article really is a summary of what had been done up until that time in terms of using these new methods, these machine learning methods in econometrics. And he gives this, in this article, there's this sentence that says, my advice to students is to go to the computer science department and take a class in machine learning. I then did that actually following this, and so that's also why I'm here. I gave a few talks about this, and this is, I think, something that is really interesting, an area where a lot of new methodological work is going to happen also in the future. So what is really new about big data? We just heard earlier that there are many different definitions of big data, right? And one of them that is out there is about the data that is being produced at a large volume, unprecedented variety of variables that we are collecting data on, and at an unprecedented velocity. All of that coming down to the fact that more and more human interactions are being played out in sort of the digital sphere, are digitized. That produces data, right? And now this data suddenly it's interesting for social scientists, for economists, because it's data on human activities at a scale that we did not have before. That's interesting in itself. Of course, a lot of the discussions that we are having and that we have had were about this. But from my perspective, what's really new and interesting, of course, is that it's not only about the data, it's about the fact that suddenly in social sciences, we now have computational social sciences. We now use these new methods, computational statistics, artificial intelligence, machine, statistical learning, data science, all these terms. We use all of these things to make sense about human activities, right? That's really what I think is really interesting, because of course, new data is interesting in itself, but it's these new methodological approaches that are different from what we have used before in econometrics, or that was the standard in econometrics at least before, that I think make this field so interesting. So what exactly is statistical learning and machine learning, and why is that different from sort of classical econometric approaches? And I think it's quite important actually to talk about this briefly at least, so that it's clear why also then the problem appears in terms of how machine learning can help for causal inference, right? So in a very general term, statistical learning can encompass everything that is, that we do about understanding data. You find that definition sometimes. That, of course, is not very helpful, because it also can refer to things such as regression analysis, right, or just descriptive analytical analysis of, any data. What's really the new thing is that I think is that since the 1980s, this statistical learning area has emerged as a new subfield in statistics that has a slightly different approach to solving estimation problems than the traditional approach that we use in econometrics. What's this difference? So from my perspective, really, the thing is that when we have an estimation problem, in economics or in econometrics, the way that we approach that in very rough terms is that we make assumptions about data generation processes, very often about linear data generation processes and distributions of the variables that are involved there. We derive often closed-form solutions to these estimation problems, the beta hat of the OLS estimation. And we employ a frequentist approach to hypothesis testing. So we make assumptions about the data generation process, about the distributions of our estimators that we get from this process. And by doing that, we can do hypothesis testing, right? So with these assumptions, we can say, well, we think that this is how this estimator should behave. We can test whether this coefficient that I estimated is significantly different from 0 or not. And thereby, we can say something about whether a certain variable has a statistically significant effect, at least, or is significantly related to the outcome variable. The computational, these statistical learning methods have a different approach, right? These computational methods solve estimation problems by exploiting computational power in combination with resampling methods. That's very important. A lot of the estimation, a lot of the process of finding the right model to estimate or to predict something is based on resampling methods. And I'm going to explain very briefly later on what that really means. They derive highly nonlinear algorithmic solutions to these estimation problems, and they make very little assumptions about the data generation process. These are sort of three important characteristics I find of these computational methods that differ quite significantly from the approaches that I, at least, learned at university in econometrics. So just a little bit of taxonomy. There are also two different, you can separate these problems that machine learning approaches or statistical learning approaches try to solve into two groups. One of them is supervised learning, and the other one is unsupervised learning. The large majority of problems that we deal with are about supervised learning approaches. Supervised learning here really just means that you have data on both, that you fit your model with data both of your outcome and your explanatory variables. And when you have that, you can learn something about the relationship between the two by looking at your data, right? So regression analysis would normally fit under this as well, right? Because if you have your outcome variable and you have your explanatory variables. The point of unsupervised learning from the statistical learning perspective very often, though, is that you use this observed data to fit your model, but then to make out-of-sample predictions. Yeah? So that's one of the key goals. And the other one is to regularize. What that means is you want to identify the variables that predict your outcome in a very good way. Yeah? And you can learn about these things by having data both on your outcome and your explanatory variables. There's also a field that is called unsupervised learning, which is slightly different, where you have just variables or information on your sort of X variables or certain features, and you let the machine learn about relationships between those features to find structure in the data, to summarize the data. The majority of the applications that I have looked at and what I normally look at is, are methods and, in the area of supervised learning. There are a lot of different approaches that can be used in supervised learning to deal with such prediction and regularization issues. I'm not going to go into detail now. I just want to mention a few, and I just want to emphasize one important point. So one method, for example, that has been mentioned before in the discussion as well is that our so-called regression trees, which can perform quite well in order to solve nonlinear prediction problems. As I said before, resampling is one core component of these statistical learning methods. And resampling is used here in this case to tune basically your regression tree, to know how many variables you should use and how to use them to predict your outcome very well. Other methods that are quite well known are, for example, lasso regressions. Lasso regressions can be used to regularize. They can be used to identify variables that predict outcomes well or that are significantly related with outcome variables. There are other methods called vector support machines, combinations of those. In all of these methods, though, when you read up and when you sort of try to understand what they do a little bit, resampling is always crucial to identify the best method, the best model, basically, to solve your problem. How does resampling work? I mean, it's in the basic idea behind this is really quite simple, right? You have your data set. You have data both on your outcome and your covariates. And what you do is you split your data into a training and a test data set, okay? And then you start with a certain model and you try to predict your outcome using your covariates. And you fit this model using this training data set. So you get some coefficients, for example, from this, and you take that to your test data set and try to predict your outcome there. That's an out-of-sample prediction. And you will have an error, right? Because some of your predictions will not be correct. Now, you use this test data set to assess how well you are predicting your outcome. And cross-validation really means that you do that many times. So you split your sample randomly into different subsamples, different training and test data sets. You do this very often, and what you get at the end is a measure of how well your model is performing on average to predict outcomes out of sample, okay? And you can do that many times, and you can do that, of course, for different models, for different methods, different prediction methods. And the idea in the end is that you choose to solve your estimation problem, your prediction problem, whatever you are dealing with. You choose the model that works best with basically using this approach to assess the performance of your model, right? So you do cross-validation, you check on average what's the error that my model is producing, and then you choose the model with the lowest error, right? The reason why I went through this here on this slide is that I want to emphasize again that this is an entirely empirical method of choosing your best model, right? Note the difference to the classical econometric approach where you would have your data set and you fit your regression in there. You make certain assumptions and sort of that's it, right? But here what you do is you empirically try to find the best predictor or the best model that solves the problem, the estimation problem that you are currently facing. So, and this has implications for causal inference. I'm going to talk about them in a second. So I think in terms of strengths for statistical learning from this perspective, I mean, it's very clear that out-of-sample prediction and regularization using this empirical method works very well, right? I mean, there are many examples where prediction works very well and works much better than, other econometric approaches that I know of. These different machine learning, statistical learning methods that work empirically can be combined to very strong predictors and artificial intelligence networks, of course, that can be, that have shown to be very powerful. And they are extremely powerful, of course, with very large data sets, right? So the larger your data set, in a way, the better this empirical method of finding a good predicting model works because you have a lot of information to use. But so what about inference and in causal inference, which is what we or I am particularly interested in, right? The problem there is that despite the fact that you might be able to predict outcomes very well, these methods, because the way that they work, they won't necessarily give you estimates of certain parameters. What I mean by that is that if you have a regression tree that predicts your outcome very well, you will not necessarily from that get an estimate of how well of the relationship between a certain variable, explanatory variable, and your outcome. But that's something we're very often interested in, right? And these machine learning approaches don't directly give that to you. Yeah? It depends on what you look at, but in these very nonlinear methods, that you won't necessarily get that. Also, there's no direct interest in the underlying data generation structure, and that's problematic because this structure is interesting from a theoretical perspective, right? We might sometimes want to know how these variables relate to each other and how they relate to the outcome, right? What's the structure behind that? It could be, because this is this empirical process, it could be that two very different prediction models that you fit using cross-validations perform similarly well in predicting, okay? But it could be that they contain very different variables, very different covariates. Now, what is the truth behind that? So which variables really should you include from a theoretical perspective in terms of explaining the outcome? That's not clear. And finally, of course, the issue is that prediction is not causal inference. I mean, when we think about causality, when we think about dealing with selection bias, with the counterfactual problem, just predicting an outcome doesn't necessarily directly help you with solving this. But that's what we want to do in impact evaluations, right? So that's why also in this panel discussion that we had earlier, there was this very clear statement about, well, these two things are different. You know, big data analytics tries prediction, and we do something else in impact evaluations. Now, I'm here to argue that actually that's not quite true, and that there is an emerging literature of how still to use the strength of machine learning approaches in such situations where you want to do causal inference, where you have a experimental or quasi-experimental impact evaluations. I want to emphasize this article that just came out in the Journal of Economic Perspectives in spring 2017, which is called Machine Learning and Applied Econometric Approach. And that's really, it summarizes really quite well also what I'm going to be talking about now. So if anyone is interested in this, please, have a look at this. I think this is it's a very good review article on this topic. What approaches can we find in the literature where these different methods are being combined? And I want to present three main sort of areas where research is being done, and then I want to go into a bit more detail on one of them, because that's something that we have tried out in our work at OPM. So the first main area is that exploits the idea or the fact that in many cases, causal inference from an econometric perspective involves sub-steps that are, like the methods that we employ involve sub-steps that are very close to prediction problems, right? And when you have such a situation, you can, of course, employ the strength of machine learning in predicting things well in order to then solve your final problem of causal inference. One example is instrumental variables approaches. Very simply, you have your outcome, you have endogenous variables, you have your instruments. The way that causal inference works is that you use your instruments to explain exogenous variation in your endogenous variables. So you try to predict that, and then you use that to infer causality in the final step. In this first step, the goal is to predict this exogenous variation very well. And there have been some papers out there where machine learning has been employed to do this first step in a good, and rigorous way. So that's one example where you can use machine learning to get to, rigorous causal inference in the end. The second thing is that in theory, you could also try to predict counterfactuals, right? There are issues around that, because what do you do with your covariates? Are they related to treatment, for example? If they are, then predicting the counterfactual might be biased. So there are a lot of different problems with this. But if you have, I know of examples where people have done that using a time series approach. So you have very thick data. What that means is like data with a long time horizon, very high frequency. You might be able to use machine learning approaches to predict how this time series evolves over time without any intervention. And then there's still a cut in the middle, and you compare your prediction to what actually happened, right? This paper by the UN Global Pulse there, this project actually does exactly that. So that's the first area. The second area is actually, which is quite interesting, but that's something that I haven't really looked into in much detail yet, and that's in the context of experiments. So you have a randomized control trial, yeah. So you're basically your causal inference is derived from exogenous assignment of treatment, but you can still use principal data mining, something like regression trees, to identify heterogeneous treatment effects and assess the robustness of your estimates to certain variations in the models, even in the context of randomized control trials. I just want to refer to the work of Susan Athey at Stanford, because she is working on this quite a lot. I find this very interesting because principled data mining to find heterogeneous treatment effects gets around the problem of multiple hypothesis testing. So gets around the problem of just basically checking all the covariates, all the background characteristics of individuals and just checking whether your treatment effects vary there or not. They will by statistical chance. Getting around that with data mining, I think, is a quite interesting approach. But the issue, or the area that we really look at, and where we have been playing around with these approaches a bit, is where we have used regularization, so the strength of machine learning to identify variables that are significantly related to certain outcomes. So where we have used this strength to prevent model misspecification in quasi-experimental evaluations. So I'm going to explain what the problem is here briefly, and then I'm going to talk about examples of where we have tried to use that, and how we've tried to do that. So the example is taken, so the work, the academic work on this is done by people at MIT, and the example that I've taken here is from a paper by Viktor Chernozokov, and to summarize, or I'll try to, I still have some time. I'll try to be quick, but there's this paper which is quite famous by Acemoglu, Johnson, and Robinson from 2001. It's called The Effect of Institutions on the Wealth of Nations. What these researchers have tried to do is they've tried to identify the effect of institutions on GDP per capita, and they've used an instrument which is early settler mortality to do that, right? Now, whether this whole approach is really the right one, that can be discussed, but the point that I want to make with this example is that your results, the results of this study change depending on the covariates that are included in the estimation process, right? So basically, you have these three variables. There were also a couple of covariates that you could include in your estimation, basically latitude, so the latitude where certain countries are placed on the globe, and continent dubbies. And you can transform these covariates as well. So you can create interactions, you can do all kinds of things with these covariates and put them into your estimation. So when you do that, when these researchers did that, these authors, what happened was that the significance level on the effect that they estimated disappears, right? So suddenly this finding that they had, that there is a significant relationship, disappeared. Now the question is, can we drop these flexible controls or not? Yeah, can we do that or not? And if we don't, it could be that we are actually committing omitted variable bias, so that we are excluding some covariates that are important to control for, and that therefore the result that we're getting is actually biased. What these authors suggest is that you can use a double selection process using machine learning. Basically, you run a machine learning approach, run a machine learning algorithm, both on your outcome and covariates and on the instruments and covariates, and you only include variables, the covariates, in your estimation procedure that the machine learning algorithm tells you are important, essentially. In this paper, they present theoretical and empirical evidence for a general finding that this approach actually works to deal with unconfoundedness, so to control for covariates in the context of such an exercise. So when they do this, the significant effect reappears again. But the point really is that I think that this approach can be applied to many quasi-experimental evaluations that we implement more generally. And that's because in practice, many impact evaluations rely on unconfoundedness. So if you think about this, not a context of an experiment, but context where you cannot do an experiment, so no randomized control trial, but where you assign treatment in some other way and you're saying I'm controlling for covariates and all the relevant covariates so that in the end, the estimate that I get on my treatment indicator really is an unbiased estimate of my treatment effect, right? So the argument always is I'm controlling for everything that is relevant, and therefore the estimate that I'm getting here really is an unbiased estimate of my treatment effect. And this includes many popular methods, right? So for example, propensity score matching, that's one of the methods that is employed very often in the context of quasi-experimental evaluations. And their unconfoundedness, this idea that you need to control for all the variables that are driving selection bias, is very important. So what I'm saying is that selecting the right covariates is important to derive unbiased estimates of your treatment effect, right? But I think that in the past, when you look into the literature, that selecting covariates and like controlling for them in the right way and which ones to select, doing that in a principled way has not been one of the key things that people have paid attention to, really. I mean, there are different approaches that have been implemented to select covariates. I mean, people use theory or deep knowledge. So, you have an expert in a certain area, and the individual says, well, I know that we need to control for these covariates because those are the important ones. They might be biasing my results. Then we need to control for them to control for selection bias. But I think that that's very difficult and, well, potentially dangerous. We've seen before that omitting variables can, of course, change the results that you get, right? But also, in many of the evaluations that I work on, at least, I deal with survey data, right? So household surveys, let's say, where we ask questions to the household head, to another household member. We ask questions about consumption, very long, consumption modules. So we have data on a lot of covariates. Now, which ones of those to select, that's, I think, not quite clear. And in addition, these variables, these covariates, can also be combined and they can be transformed, right? So it could be that selection bias is driven by non-linearities. So you can interact covariates with each other. You can transform them to polynomials, things like that. Now, which one of all of like this huge bunch of variables, which ones to select is, I think, not an easy question, not an easy question to solve. What traditionally, was done, I think, was to run estimations showing different specifications, so you show robustness of your estimates to changes in the covariates that you include, which can be one approach. But what we have been trying then, based on this literature that is emerging on this double machine learning or double selection process, is to use both theory but also algorithmic approaches to select covariates to ensure that we have a principled approach to select covariates to control for selection bias. And so I just want to give an example of propensity score matching and how this was implemented. As I said before, propensity score matching is one of the key methods that one of the methods that is used very often that relies on the unconfoundedness assumption. And again, what that means is that you need to control for the right set of variables that are related to, that are driving selection bias. The approach that we have been playing around with is based on this double selection machine learning literature is actually quite straightforward. I mean, for the first step of your propensity score matching approach, you need to find these right covariates. So we run algorithmic selection approaches both on our treatment and our outcome variables using baseline data mainly to identify the right covariates, right? We repeat that including transformation. So you have a very large set of transformed variables, interactions, polynomials. You include those as well. And then you use those in the second stage. Well, you use those to predict your propensity score, and then in the second stage to match on that. And then, of course, after that, you do balancing tests. You do all the sort of controls, of course, to ensure that what you are actually doing shows, or that your estimation procedure shows the right balance, for example, to ensure that you're doing the right thing, of course. So that's very briefly sort of the procedure that we go through in order to derive this propensity score matching approach. I want to end with 3 main points. I think I mean, as we've seen before, there is the whole data science, big data analytics discussion, machine learning discussion, and there's, econometrics, there are problems of causal inference. I think that these two things, of course, will be separate, and there will be separate problems where one or the other can be used, right? But I also think when we look into what's happening in departments and universities, what's happening in the literature, I also think that these methods are going to mix, actually, and that classical econometric approaches will be mixed with computational methods more frequently for inference purposes, actually. As I said, much of this is still in academic departments, but it's also slowly feeding into more applied, mainstream applied work, actually. And what Michael Bamberger earlier said, that evaluators need to sort of learn about these new approaches, I think that is actually happening. I mean, when you look into papers that come out on, in development economics as well, you slowly see that these approaches are being used more and more in the empirical strategies. The promising areas that I see is just a summary again of what I mentioned before. So I think there is something about predicting counterfactuals, and that's partly because you can also, that depends a bit on the data that you have in hand, but if you have very thick, strong big data, you can use that. There's the whole area of instrumental variables, which I think is very promising in the context of RCTs, identifying heterogeneous treatment effects, which is very interesting often from a policy perspective. I think doing that using principal data mining can be very promising. And then finally, what I've been talking about a little bit at the end, in quasi-experimental and observational studies, so in studies where we don't have experimental experiments, I think that preventing model specification is very important, and that doing that using, or at least taking machine learning as an aid there is very promising as well. So that's what I want to end with. There is some time for question and answers. Thank you very much.
Thank you very much, Paul. I'd like to open the floor for discussion. We have about 25 minutes, actually.
Oh, yeah. That's faster.
I'll take 3 questions at a time. Yes? Self?
I'm tempted, given your last slide, to say we need more dragons and a bastion. Sorry, I meant to switch on. You made no reference at all to some of the Santa Fe work on complex adaptive systems theory, the work of people like Brian Arthur, which would basically challenge the whole concept of causality anyway. Mm-hmm. Yeah, and they would fundamentally threaten RCTs. If you look at the more recent stuff, say the Donuts economic stuff on working within constraints, yeah, I think all of that challenges a lot of the machine learning concepts, together with the danger of ignoring outlier events. Mm-hmm. Yeah. And outlier events are key to actual change, particularly when you're dealing with resource constraints. Yeah, the lack of sustainability, the need to radically repurpose existing technologies for novel purposes. Yeah, and I mean, I'll talk about this tomorrow. But one of the things we know about human evolution is the ability to see things through abstractions, allows us to make rapid, unexpected connections. And actually, machine algorithms don't do that, because they're entirely dependent on the quality of the human training data sets you feed into them. And those training data sets tend to be selected entirely on current knowledge of past practice. And therefore, I'd be dubious about your counterfactual point as well.
Okay, well, thank you, David. I think I was going to make a similar point. You've made it much more articulately than I could have hoped for. I think it's pretty much that. It's the danger I've seen before, and I've always seen as well, that's although this could work, it's got the aforementioned problems, obviously. But even last year, I mean, I do evaluations, I recruit consultants as well to do evaluations, and you see this all the time, that this almost creates a narrative that people think that they have to follow, but the capacity isn't there at all to do it. And so in the end, people start fudging it. I mean, for example, even last year, the two of the evaluations that I recruited for, the consultants, I mean, I sent them a TOR, came back, and for some reason they thought I was expecting something that I wasn't, and sort of they didn't realize I was more cynical than they thought, and sort of they came up with this sort of crazy thing which I'd had to push back and said, no, you're not going to be able to achieve this, you haven't got the capacity, and sort of redo it. And basically that's what happened. Sort of, it's completely underestimates the lack of capacity that there is, especially in the INGO sector, to do this kind of stuff. In the end, things get made up, and it doesn't help anyone because then the reports that get produced are useless. So I think it's something that has to be considered.
Any more questions?
Thank you very much for that presentation. It was kind of mind-blowing and confusing at some points, but
I'm sorry for
thank
that.
you very much. My question is around just to be sure I understood things very well, where you did say that machine learning can actually help us to be able to make some conclusions about causal inferences when we have only been able to just talk about relationships. For instance, I've been trying to study undernutrition in Somalia. That's a place that I quite work a lot. Looking at maybe about 10 years of data that has been collected around malnutrition and together nutrition and food security data, trying to understand the trends and the predictors over a long period of time. What we can see at best now is that we can only draw relationships and just say these things are related. Are you saying that from machine learning we can actually get into the sphere of causal inference?
Shall I? Okay, I'll start from the last. I'll take the last question first. So first of all, apologies for being confusing a little bit. I hope that I can perhaps clarify things a little bit with this answer then. So my point really was that machine learning in itself, the methods that are used, that I know of at least, don't help us with causal inference. And that's because, as we said before, the goal of machine learning often is to find either good predictions, out of sample predictions, using information that you currently have to try to predict something for tomorrow, for the next time period, or out like into a different area, for example, or to find relationships. Yeah. So when I talk about regularization, what I mean is finding variables that explain other variables very well, right? So that's basically finding good predictors in a way. Solving both of these problems doesn't help you with causal inference. I mean, it doesn't directly tell you whether there is a causal relationship between two variables just because they are related to each other. Now, of course, there's a very long history of thinking about this, and that's where the the concept of causality and counterfactual, of course, comes in. History of thinking about this issue, right? How do we infer causality with data that we can observe, like not in the context of experiments? What I was saying is that I think machine learning can help us with methods that we already know of, yeah, to make kind of these methods better or more robust. That's my point, right? And so where you couldn't infer causality before, machine learning might not necessarily, solve that issue. Yeah? But where you could perhaps try something before, machine learning might help you to do that in a better way, in a more rigorous way. Okay, so the whole concept of causality in that sense of like having counterfactuals and trying to approach counterfactuals to compare them to observations that have been treated, for example, and therefore to infer that the difference is the treatment effect, that I would still say holds within this framework that I've been presenting. And so, I mean, to sum up, I think machine learning is slowly coming into our research methodological toolbox, essentially, and it might help us to do things better, but it's not going to solve basically situations where before we couldn't do any inference at all. I don't think that's the case. So that might not be a very positive statement, but I think that's the issue. But so then coming back to your comment, I mean, you were referring to the whole framework of causality, of course, that I was operating in. And I don't know the literature that you were referring to very well. Of course, I started this presentation under the assumption that many of the evaluations, impact evaluations that I as a consultant need to work on and that clients would like to implement fit very often into this framework, right? It's often about whether a certain intervention has made a difference or not, and the tools that we use from sort of that we pull out of our econometrics or economics toolbox always employ this counterfactual framework, of course. And so, and that's sort of the perspective from where I come in and where I want to see whether machine learning can help us with this. But whether there's a different concept of causality where machine learning can perhaps help even more, I think that would be very interesting. I would be very interested to hear more about that. You were referring that perhaps tomorrow there's going to be something about this. In terms of the capacity, I think that's your comment on capacity. I mean, I think that's, of course, very true. I think that, as I said, slowly training is, like, at least from what I know, is that courses at universities in training institutions are picking this up. And I think this is becoming more mainstream, right? I think that this is becoming in the sense of, like, if there is someone who has the technical capacity to implement a quantitative research project like this, this individual will have been exposed to these new machine learning approaches in the future. I think it will be much more likely that they will have been exposed to these approaches. Yeah, sorry.
When I talk about capacity, I don't necessarily mean knowledge. I mean, I have an economics background as well, although I switched from that very quickly after my undergraduate because I lost faith in everything I was being taught. But it was more about resources, able to do it. I mean, last year, for example, there was a DFID-funded project which we were going to do evaluations on. My manager was still around at the time in 2013. He decided it was going to be a randomized control trial. I tried to push back on it for ages, said, no, it's not going to work, please. This is going to go horribly wrong. He wouldn't listen. It went horribly wrong. And a year and a half in, he left, and I was left to pick up the pieces. And so I think it's almost personal in that kind of way, given the experience. But really, within INGOs, and we're not a small INGO, Islamic Relief Worldwide, we're a relatively big one. But we're an evaluation team of 2 people. Mm-hmm. And so something like this, especially given for managing 40 teams, it creates a reality on the ground that it just cannot be met. Not at least not internally anyway. Mm-hmm. Externally, it might be a different thing, but sort of it just creates a norm that just becomes difficult, and then people try to meet that and cutting corners in order to try and make it look like it's good, but it doesn't actually achieve. And in the end, I had to do a similar thing last year as well. I mean, sort of, and yeah, it's sort of I got away with it. But I knew it wasn't ideal. And to be fair, I was honest in my report as well. I said, this is what we were going to do. This is all I could do. Like 95% relevance. I needed to interview 374, I think it was 374 beneficiaries. At most, with a team of 3 people I had, we were able to do 140, I think, across a week and a half, 2 weeks. And that was nowhere near the 95% statistical relevance. And that was with just killing ourselves doing it as well. So we have to be sort of, especially within INGOs, it's just something we've faced before. And that's why I'm pushing back, because it's sort of it's extremely difficult then. Yes.
So there was a gentleman there in the back first, and then 2 questions here. Please introduce yourself. Yes.
Yes. Hi. Can everyone hear me? My name is Gaurav Singhal. I'm a data scientist at WFP, and actually, this is more a comment than a question, because I've been really exploring this idea of using how to do causal inference with machine learning. This area actually has had a lot of active development in the last 1 year or so, led by MJ Vanderland at Stanford and Dr. Sherry Rose at Harvard. And there's a technique called targeted learning that allows you to do basically quasi-natural experiments, simulate them, using natural experiment information. So you could, you have some grouping of people that receive some treatment, and then let's say the treatment is indeed endogenous to the characteristics of the people. You can tease out the treatment effect using the targeted learning technique, which allows you to basically compute these incredibly intricate probability distribution functions using machine learning, and so. I think there is actually a possibility for us to really now, using these kinds of techniques to extend them and actually start doing real causal inference, in this domain. And that's really all I had to say. I wanted to kind of share that with the rest of the community.
I'm Simone Lombardini from Oxfam. Thank you very much, Paul. It's a very fascinating presentation and really, really interesting. And thanks also for sharing the example of you're working on in using regularization to prevent misspecification. And I was wondering something also related to the comment before. Is there any requirements in terms of sample size that is needed in order to do this exercise? And secondly, what is your take between a model that is built based on the information you have on coming from the ground and coming from the literature versus a model that is built with this technique? If there is a discrepancy, where would you put your faith?
Thank you very much for the presentation. Aslıhan Arslan from the RIA Division, Senior Economist. Actually, okay, excuse my ignorance first. I don't know how these models work. I don't know who writes the program behind machine learning, but I'm assuming there are humans, right? So my question is then, okay, so you talked about the heterogeneity, heterogeneous treatment effect opportunity that machine learning provides us. So we've always done data mining, right? Now it sounds like we were doing it unprincipled somehow. But so I'm wondering, so the people who write these programs to make it principled, what's the difference? I mean, if a person is writing the program, just the fact that they can churn data in much more, like really systematic ways and in huger quantities, then we could just, you know, okay, you look at, I don't know, 100 observations, 100 variables and thousands of observations. Of course, our brain is limited. So this is just taking what we were doing to a different level, but doing the same thing, right? Does that make it principled versus unprincipled? So this is just a maybe general question about the whole thing. Thanks.
Okay, yeah.
One gentleman there, and then
Okay.
we let the chance all to reply.
Right. So this is David Gennady from TechnoServe. We're doing some work right now on decision science, in particular aspects to do with, in this case, soil quality as a predictor of productivity and that kind of thing. And I wanted, it seems like, I'm not an expert in decision science by any stretch of the imagination, but it seems like the kinds of principles that are being brought to bear are directly pertinent to the kind of approaches that you're bringing. For example, the use of machine learning to establish which variables are the ones that are the key drivers of. In this case, it's a causal model, but I think the same principle will apply. Maybe can you talk a little bit about how the two are related and how those techniques may be brought into a decision science model, which is only different from the regular models in that it takes a stochastic view. So rather than producing a single result or relationship, it provides a distribution of potential results based upon, I believe, a decision science approach. Sorry, an approach based upon multiple runs. They use a Monte Carlo trial, which I think is based upon using machine learning and existing data on relationships between key variables. Please, I'm not an expert at all. Please tell me how the two are related, if you can.
Shall I go? Yeah, okay. So, yeah, first of all, thank you very much for the targeted learning comment. I think that's very important to keep in mind. Of course, what I presented here was a snapshot of what I found in sort of the last year, basically, and what approaches that I have, come across, and that I think are interesting in the context of impact evaluations in developing countries, where very often we use survey data, right? So, and so that's a very specific area, of course. I think this whole field is developing very quickly, of course, and many new approaches are being tested also in other fields that are not directly necessarily related to this, right? But that where methods then can, at some point, of course, sort of come back into our work. So I think, yeah, thank you very much. This is definitely something to look out for, and I think there, like, the frequency with which we will see new approaches being tested and presented, of course, is also going to increase. That's the first thing. The second question was about sample size and model discrepancy. So in terms of sample size, some of my understanding is that some of the machine learning and statistical learning approaches really require large data sets. And what large means, I think, depends on the problem that you're looking at and depends on the type of data that you're looking at. But actually, for some other approaches, for example, like the Lasso approach, which is where originally you would, which is a penalized regression, where originally you would set your penalization value using cross-validation, there's a theoretical argument for how to set this. What I mean by that is that it's not dependent on your data anymore, and you can set that and use Lasso in very small data sets as well. So the example that I showed on the effect of institutions on wealth, actually, this is run on, like, I don't know, something like 80 or something like that, n. So the number of observations is quite small. Yeah. So you can use Lasso actually that's why we found it useful in contexts where you have survey data, so large number of variables and sort of, reasonable number of observations, which can be 300, 500, or even less. I mean, it's really, really quite flexible. But my point really is that it depends on the method that you're using, I think, and you need to, that's what I would answer to that. Model discrepancy. You were saying what happens if you have a theoretical model and you have one that has been derived algorithmically in a way. Well, I mean, that's a difficult problem, and I don't really want to answer that question. But what I would say is that the problems that I have shown, or the situations that I've shown where machine learning might be useful in our sort of work, these are situations where we don't mind that much about the underlying model, right? So because we don't care about interpreting the underlying variables. We just care about having a good predictor or having controls for everything that is relevant, right? And so and that's where we come back to, that's where then the nature of machine learning comes in again, right? So where it's about really empirically trying to find out what are the variables that are relevant and trusting your algorithm in a way. And I think the nice thing, well, I mean, I think these are contexts where you don't care about the interpretation. That's why I would prefer actually this, because it ensures that it's not driven by any biases that I have, that I, as a researcher have, but it's really driven by sort of an algorithm that I understand, right? And therefore I would trust that. And it's also replicable and everyone can test it, and it's really sort of open in a way. So that's this answer. And it goes slightly into, this answer goes into the principled and unprincipled data mining. I mean, I think that's a very, I guess, fundamental question, and I would find it difficult to answer that in a very fundamental way. But I do think that the good thing about this is that it's like, in terms of data mining, in terms of using machine learning to identify these things, testing these different approaches, is that, as I just said, I mean, this is a very sort of open and understandable way of how we do this, right? These algorithms are written, of course, by the researcher, or at least are thought about by the researcher. It's very clear and open to everyone how this process comes about, and so I think that's much more, in a way, it's more open and honest than perhaps data mining that was previously done, sort of testing different models and then just publishing 2 or 3 of those, right? So that's why I think this is actually much. That's one appeal that I find in this, and the other thing is, of course, that I think there's evidence for the fact that this machine learning, data mining, using machine learning approaches, that it works very well, and that it produces approaches that produces estimates and predictions that are very accurate and very good, right? Compared to many other approaches, which give lenses, of course, additional credibility, I think. So the final question was about the relationship with decision science, I think. And I have to say that I can't answer that really, because I don't understand much of this area of research that you just mentioned. The one thing that I did pick up, though, and I think that's what I want to say, is that yes, machine learning approaches, when they are very good, as I said, in like problems that are about prediction, but also in problems of regularization. And what I mean again by that is identifying variables that predict or that are related to certain outcomes very well, right? And if that's a core problem of the research that or the analysis that you try to do, then looking into machine learning approaches and trying them out, I think, might be a fruitful way forward. Yeah.
have a comment myself, because we're speaking about causal inference, right? And but this is the problem we're plagued every day, right, with impact evaluation when you use observational data, right? What is the truth, right? If you don't have a pure experiment, right? So you want to leverage on the potential large data sets, maybe to uncover this truth with a lot of cross-validation. So it's really, for me, it's really how the problem is, how do we bridge the gap between the two disciplines and bring the two disciplines together, right? And have a data scientist talk to the social scientists and the econometricians, and just bring it together so that we understand each other and we leverage on each other, basically like, I don't know, competencies and added value, right? Because at the end of the day, also, when we estimate our models with our data, we have problem of selection on observable, on unobservable. And actually, I really see these added values on leverage on a massive number of covariates and not knowing which one is the best to identify the counterfactual. So having powerful, validated algorithm can be really, really powerful, right? But the problem is, of course, we need to emphasize supervised learning, but yes, with a bit of hypothesis testing, right? With a priori knowledge about what the truth could be. So I think, like, in terms of decision, I'm thinking, what about maybe machine learning can be useful for data-driven decision making when I'm agnostic, right? But again, with a bit of caution. But yes, these are my thoughts. So the takeaway, because I have to conclude, I'm afraid. So I would say, let's embrace innovation, right? Because this is exciting. We need to leverage on large data sets. Although at IFAD here, we're still concerned with small data sets. I would say we want to evaluate the impact of our project, understanding whether a policy works. So we're primarily in a small, like a small n, right? So small data still, but maybe in 20 years or maybe less, we can move to big data. No, I'm joking. But yes, so embrace innovation. So I see the potential of machine learning. And yes, and the major takeaway is really that machine learning can really provide a new set of tools for estimating causal effects in a high dimensional settings. So thank you very much to everybody for your participation, and to Paul. And thank you.
Thank you very much.